Yeah, morning everyone. So my name's Kat Scott. I'm a researcher up at the University of Leeds. So I know a few of you already, but great to meet the rest of you today. I'm going to be giving, similar to Alex, a bit of a brief introduction to aerosol modelling with UKCA. There's so much detail in terms of, once you start to get into whichever particular bit of chemistry or aerosol that you're interested in, it's impossible to cover all of it in one introductory lecture. So this is going to be a bit of an overview, hopefully point you in the right direction for things that you want to find out more about. I want to just give a quick acknowledgement, particularly to Kirsty Pringle, who has given this lecture previously, and I've based some of my content here on things that she presented. So thanks very much to her. So I wanted to start with just a bit of an image of how aerosols kind of look on the global stage. And I'm actually going to just see if we can watch that. So this is an image that NASA put together just to show how aerosols are moving around in the atmosphere. And they've used different colours to represent different kinds of aerosol species. So we've got kind of organic matter in green, dust in orange, sulfate in white, and sea salt in the blue colour. And I wanted to just start with this because I think it really nicely illustrates that all of these aerosol particles they're coming from somewhere, they're being put into the atmosphere, but they don't stay in the same place. They're getting moved around by transport. And you can see that wherever you are in the world, you're going to end up with aerosol particles that have come from other places. So that's really one of the reasons why we need to have these global models to understand aerosol and what's going on. Similar to the chemistry, it's not just a case of understanding exactly what's happening in one location. You've really got to know what's going on elsewhere and how much of that is getting moved to the place that you're interested in. So as well as being kind of nice to look at in a global sense like that, there's lots of reasons why understanding aerosols in the atmosphere is important. The first two I want to just focus on are what we call aerosol radiation interactions and aerosol cloud interactions. These are the main ways through which aerosol particles in the atmosphere are affecting the climate in particular. So by aerosol radiation interactions, I essentially mean a bit like Alex and his experiment with the light passing through some liquid or a gas. Particles in the atmosphere are also interacting with radiation. They can either absorb it or they can reflect it. So their presence in the atmosphere is it's a really important part actually of the Earth's energy balance. The aerosol cloud interactions it kind of represents the range of ways that particles in the atmosphere are influencing the formation of clouds, the lifetimes of clouds, the brightness of clouds, essentially. So that is another important way that they are affecting the climate. And I just want to focus on those two initially, because in terms of our understanding of climate and climate change, the role of aerosol particles is one of the big uncertainties that we still have. What this chart from the IPCC is showing is we've got things like carbon dioxide and other greenhouse gases at the top. I'm sure this is something that people are quite familiar with. But we've got those kind of big positive radiative forcings from the greenhouse gases. So this is all representing the change that's happened basically since the pre-industrial period to the present day. So in terms of greenhouse gases, we've got positive radiative forcings because the concentration of those has increased and they have a warming effect. There's lots of other stuff going on, but you can see down at the bottom in this blue bar, the two blue bars, these are the aerosol cloud and aerosol radiation interactions. And you can see that they're some of the only things that actually give us a negative radiative forcing. And what that means is that since the pre-industrial period, the aerosol that we have put into the atmosphere has had, actually, on balance, a cooling effect on the climate. And so this kind of total radiative forcing we end up with, it's a combination of all this positive forcing from the greenhouse gases and the negative forcing from the aerosols. And I'll come back to this at the end because it's quite important for how the climate's going to evolve in the future. Understanding how much that is going to change is going to make quite a big difference. So you can see, firstly, that there's the kind of the lighter blue bar for aerosol cloud interactions is the bigger of the two. It's the stronger forcing than the aerosol radiation interactions. But you can also see this big uncertainty bar, much bigger than any of the other elements of the climate system. And it tracks through to give us quite a big uncertainty in the overall radiative forcing. So this, our ability or our lack of ability to really constrain exactly what's been going on with aerosols over the past 150, 200 years really limits the extent to which we can pinpoint exactly how much of an effect humans have had on the climate. So hopefully that gives you a bit of an idea of why developing something like an aerosol model, including it in a global, whatever kind of framework you're thinking of is really important. And just to go back to some of these other reasons why we might want to model aerosol, Alex kind of took us through the basis for how we can think about atmospheric chemistry happening in the atmosphere, but some of those chemical reactions actually rely on having an aerosol surface area, an aerosol surface on which to take place. So these aerosol are kind of important for providing that. In terms of biogeochemical cycles, one of the things that aerosol particles, when they're moving around the planet, they can actually be involved in transporting nutrients from one place to another, sometimes getting to kind of remote ocean regions where they're actually a really important source of nutrients there. And health effects. I think you're going to have a talk specifically about air quality at the end of the week. Yeah. So it's less a focus of what I'm going to talk about today, but it's another reason why we need to understand the kind of accumulation of particles in the atmosphere, is understanding the impact it can be having on human health. Because we know there are connections between people being exposed to concentrations of particles in the atmosphere and adverse health outcomes. With health, what we're mainly interested in is just the total amount of particles that are essentially small enough to get into the human respiratory system. At the moment, the information we have about what kind of causes health problems isn't sophisticated enough for us to know whether it's some particular kinds of particles, coming from particular sources, or whether it is just generally the fact that people are breathing in particulate matter. So when you hear things like PM 2.5, that's referring to particulate matter smaller than 2.5 micrometers. And I'll get on to kind of the sizes of these particles in a second. So there's lots of reasons why you might want to model aerosols. It's not all about climate, but certainly a lot of the interest in understanding aerosol does come from climate. So Alex was talking about, from a chemistry perspective, how you can envisage what a model is trying to do and how you can kind of break that down into putting together the equations that you need, having the framework that you need to bring together all the different bits and pieces that you ultimately need to get things to kind of get that Lego model as good as you can, basically. And it's always about a compromise between detail, computational efficiency, and actually just what we know about reality. So in terms of aerosol modelling in particular, there are several challenges. The first one being that now we're not talking about gases that are all of a kind of similar size. We're talking about aerosol particles that can range from a few nanometers in diameter up to tens of micrometers. So when I mentioned PM 2.5, that was relating to 2.5 micrometers. So a micrometer is about it's exactly 10 to the minus 6 meters, and a nanometer is 10 to the minus 9 meters. So we're talking about things that kind of span a pretty large range. And these are some examples from typical observed size distributions around the world. So these are people have gone out and they've measured the the particles that they could find in the atmosphere. They've worked out what size they are and how many of each size there are. And I'm just showing these really here to emphasize how different they can be in different parts of the world. And the fact that you've got this range from, so here our x-axis is in terms of nanometers. So we've got, in some locations, we do have particles that are, less than 10 nanometers in diameter. And then in other places, we've got them here that are, more than a micrometer in diameter. So when we're thinking about measurements, we need a way of measuring particles across that size range. But when we're thinking about modeling, we also need a way that can capture that range of sizes as well. When you see aerosol size distributions, they're often presented in this way, dn d log d. And what this, so n is particle number, the number concentration, and d is the diameter. And it's just a way of normalizing the concentration values so that the number concentration reflects the width of the bin that it's been measured in. Because visualizing aerosol size distributions is really difficult because you've got that range of sizes, you've got different numbers present in each of those sizes, and we need to find a way of kind of getting them on a scale that means it's actually possible to see that. So these are all different places around the world, and you can see how different those size distributions are. But we also find that even if you go to the same place and you measure the particles in the atmosphere at different times of the year, you can end up seeing some really marked variations there as well. And I just picked two examples here of where that's true. So in the Arctic, we can see in this top figure, so these are size distributions from the same location, but in the winter, we can see that there's more larger particles than there are in the summer. And that's because we're getting a lot of transport from the mid-latitudes, essentially of pollution that's getting transported there. And that happens to be of that particular size, so a few hundred nanometers in diameter. In the summertime, though, we don't see that transport, but we do see smaller particles. And I'll come on to how they can end up there in a few slides. But essentially, that's because we're actually getting a local formation of new particles during that period. And so even just in that same location, we can get quite different kind of appearance of that size distribution. And on the bottom, this is an example from tropical rainforest, where you can see that in the dry season, so essentially when there is a lot of biomass burning, there's not much rain, hence the name the dry season, it's really dominated by particles of a particular size that are coming from this process of burning. Whereas in the wet season, there's lots of rain, so firstly it's cleaning the air, there's less fire, so you don't have that really, really big kind of input of these particles, but we also see some more local formation of particles during the wet season. So you can see there that we need to be able to simulate different things going on in different parts of the world, but also different things going on in the same part of the world at different times of the year. So the aerosol size distribution is, again, similar to the chemistry. It's complicated in reality. So we can try and we need to find a simple way of representing it in models that enables us to capture enough of the complexity, but be computationally possible to actually run. And so in terms of aerosol, the aerosol model that runs within UKCA is GLOMAP mode. So it's the modal version of one of these schemes. Its predecessor was called GLOMAP bin. So that was like this example at the top, where essentially that aerosol size distribution is divided up into very narrow bins of particular sizes, and then wherever you are in the world, there's no assumption being made about the size of that distribution, but the model is able to simulate the kind of number and the composition of what's in each of those bins. However, whilst this might be really useful if you're looking at a particular location or you're looking for a really short period of time, it's just far too computationally expensive to have all of those tiny, tiny bins divided up in an Earth system model. So most Earth system models, if you're looking at beyond the UK, Earth system models around the world will mostly be using modal schemes. So as I say, glow map mode that's in UKCA is one of these. So it represents the size distribution using what we call modes, represented in this lower panel. And the arrows here indicate the fact that the size of these modes and their position within the size distribution can shift. So it's interactive as the model run is evolving. And so it can capture quite a lot of the detail in the aerosol size distribution, but you can see that it's never going to capture all of the detail that you might get in a really a kind of more precise sectional scheme. In glow map mode, like other modal models, each of those modes will be tracking the mass and the number of particles that are present, and from that we can work out essentially how much of each different component that's there, and I'll come on to what those components are in a minute. And as you can imagine, this is much computationally cheaper to run, and it can be flexible as well. So you can run with different modes kind of activated, and so you can simplify it even more if you want to. There's some global models that will just have 2 modes, for example, but you're obviously then compromising a bit on the detail. So as I touched on there, particles can also vary in composition. So what we looked at in those little size distributions from around the world was simply the size of the particles and how many there were. And that's really only half the story, because those particles can be made of all sorts of different things. So again, with our global model that we're trying to build, the second challenge is how we capture that variation in composition. So this map from is showing us that essentially wherever you are in the world, the aerosol particles there are made up of lots of different components. So the main ones we've got are sulfate in red. So you can see there's lots of places where sulfate makes up the biggest chunk. Another important one is organic matter in green. So again, lots of locations where organic matter is the dominant contributor. Over the oceans, you tend to see more of this light blue contribution from sea salt. But having said that there are dominant contributors in different places, you can also see that wherever you are, there's a bit of everything. So like I showed in that animation at the start, because of the way that the emissions are being transported around the world, you're always going to end up with a mixture of local and transported sources. And so, again, this gives us an idea that we need to have a way of representing these different components, and we need to have a way of allowing them to be moved around the world. So, as I said, the glow map mode scheme is the one that's in UKCA, and that is it's modal, so that's represented by the image at the bottom here. And the top one, again, is an example of the predecessor sectional scheme, where you can see that within each bin, it's divided up into contributions from those different components. It's the same in the modal scheme, in that we can track how much of each component is present in each mode. In UKCA, there's lots of kind of variations in how you might run the model, how you might, things that you can kind of select to be included. But the framework is that there are 7 interacting log normal modes. So there are essentially, I'll come on to the specifics of the modes in a second, but there are basically one distribution of soluble modes and another distribution of insoluble modes. So that's critical, because we need to be able to keep those two separated. That's important in terms of once we start thinking about what can act as a cloud condensation nuclei, and I'll come on to that. But it does mean that the composition within a mode is fixed. So not fixed in time, but fixed in the sense that you can, all of your, let's call them 1, 2, 3, and 4, all of your particles in mode 3, we have to assume that they are a mixture of a particular set of components. So there's no variation in that. The other limitation of this is that we can't account for different composition within a species, although that's something that's quite important when we're thinking about things like organic aerosol, where we actually might have lots of different organic aerosol, but it's represented by just kind of one component that we call organic matter. So having just called them 1, 2, 3, and 4, the modes do have actual names, you'll be pleased to know. So what this schematic is showing is a kind of idealized version of those little size distributions that we saw from around the world, pulling out each mode individually. So the black line is essentially what we would have seen on one of those initial plots, because that's the total. But it's made up of a number of kind of underlying modes underneath. So the nucleation mode is in blue. As we get bigger, the Aitken mode is in red. The accumulation mode is in the kind of darker red, and then the coarse mode is in green. So the three larger modes have a soluble and an insoluble version of themselves, whereas the nucleation mode is just soluble. Everything in there is soluble. And we'll see as we go through how things can end up in those modes, how they can move between them. Do you have a question? Yeah. So everything would either be in one mode or the other, but things can get transferred from one mode to another mode. So I'll come on to that when I talk about how things move between the modes. So in terms of the model, we've divided the atmosphere up into all of these grid cells, and each of those grid boxes is going to contain information about the composition, so basically the mass of each component that's present in a mode, and the radius of the mode at that particular time, which means that you can then kind of recreate this aerosol size distribution. So this, as a size distribution, isn't being represented in the model at every time step. It's something you have to kind of take the information that is there and reconstruct yourself afterwards in order to compare it to observations, because what we actually just track is the amount of each component that's present, and from that you can then work out the size of these modes. So in UKCA we've got the sort of standard setup, although I know that's kind of a ever-evolving setup. Traditionally the standard setup has treated 5 chemical species. So we've got sulfate aerosol, which is basically produced from the oxidation of SO2 to give us sulfuric acid. That might be referred to as SO4 or SU. You might see it kind of written in either way. We've got organic matter that's referred to as OM. Confusingly, you might also see that referred to as organic carbon. They're essentially talking about the same thing, but the organic carbon is basically just the carbon within the organic matter. And the reason to just make that distinction is that if you're comparing one to another, you need to kind of scale to know which one you're looking at. So essentially all organic matter will have a core of organic carbon, but it will be associated with a certain amount of non-carbon matter as well. That's particularly important if you've got an observation, for example, from a forest that's in organic carbon, but your model tells you how much organic matter you've got. You'll need to translate between the two. UKCA also simulates black carbon and sea salt and dust as well. So this dust is something that's a little bit different depending on whether you're working with the offline version of GLOMAP mode or whether you're using GLOMAP mode within UKCA and within UKESM. So the dust is treated separately in some of those schemes. So when we run GLOMAP mode offline, it can accommodate dust and treat it as one of its components. In UKCA, I think, is still separated.
So working on making using
Yeah, yeah, okay. Excellent, okay. So dust incorporated is to come. So if you see something that's a bit confusing in terms of dust being treated separately, then that's why it's still the kind of the what's called classic way of treating the dust aerosol. So again, in the standard UKCA aerosol scheme, and again to highlight that this is sort of the framework within which you can work, so you can choose a setup that has the modes that you want, and to an extent the components that you want. But the standard kind of framework is the modes that I described, going from nucleation, Aitken, accumulation, and coarse, going up in size, so starting off at around 5 nanometers, getting bigger until we're up at the kind of micrometer scale, and then the equivalent insoluble modes, so Aitken, accumulation, and coarse, all have an insoluble version. And you can see the reason for doing that is that they can contain different components. So this is the way that we can track how different components are emitted and moved around and play a role in size distribution. So I'll come on to a bit more about the specifics of some of these processes, but I suppose the key thing to highlight here is that some species are emitted into the insoluble modes because they are insoluble, so that's how they start off. But then as gas phase species can condense on them and transfer them to the soluble mode. So that's why you can end up with components in the, we have a restricted set of components in the insoluble mode. Once things condense onto them, they can move into these, into the soluble mode. What we've highlighted here is the kind of main routes of these species entering the modes. So with sea salt, the primary emission would go into these kind of larger modes, whereas something like sulfate, it's formed through nucleation, and I'll talk about that in a second. So that's kind of where it enters the size distribution at that lower end. So we've covered the fact that there's a big range in sizes. We've covered the fact that there's a big range in composition, potentially, and we've got to find a way of tracking those changes. But there are also microphysical processes that are going to change the size distribution. It's not just a case of putting all these things in and then they're kind of static. Things move, things interact, and that's really where the kind of the fun, I suppose, of aerosol modelling kind of begins, because, and it's the reason to need to use an aerosol model, is that we don't know exactly what will happen when we combine certain sets of emissions or parameters. So I'm just going to step through some of the important processes that are controlling the size distribution. And later on, when you're working through your tutorial, you'll see kind of subroutines that have got names that will kind of ring a bell based on these processes. And I'll show you a list at the end where you can kind of see what the subroutines are called in the model. So there's, in terms of what ends up in the atmosphere, we've got emissions of both gas phase precursor gases, but also we've got emissions of materials straight into the particle phase. So in terms of gases, we're thinking mainly here about sulfuric acid, and in terms of particles, this can be black carbon, organic material, sea salt, essentially particulate material that's emitted directly into the particle phase. But we've got all sorts of other processing that goes on that leads us to those different size distributions at different places. If it was just a case of stuff being emitted and not being transformed, then we wouldn't really see that variation in those size distributions so much. So I'm just going to step through some of these key processes. So in terms of emission, there's two main ways this can be done. And again, some of this will depend on the kind of framework within which you are using the model. and the sort of, the latest developments at the time. So emissions into the model, so gases and particles that are going into the model, can either be read in essentially as a file. A bit like Alex was saying, you can find an emission inventory, download the emissions, and away you go. So you'll end up with something like a kind of a grid of your emissions per area. And to develop those emissions inventories, someone has either had to, in the case of industrial emissions or anthropogenic emissions, they've looked at how much kind of human activity or commodity use there is in a particular area, worked out how that affects the emission of something like black carbon, and then had to develop something to represent the spatial distribution of those emitters around the world. And that gives us this kind of like gridded data set of emissions. And it's the same in the natural world, in the sense that we need to know spatial distribution. So in this case, we need to know where the world's forests are. And then with natural emissions, they're more often controlled by climatic variables, in particular temperature. Sunlight can be a factor as well. So they'll have had to incorporate all of this information, again, to give us this kind of distribution of emissions. And I'm just making this point because this is where, depending on the exact kind of bit of this process that you're looking at, you might move from using something like a gridded emissions data set towards something more interactive that you've actually either developed, or you're kind of using a version of the model that is taking that information from somewhere else. So like in the example of this emissions from the natural world, you might be using the model coupled to joules, and so you might be getting some information about the Earth's surface coming from there, coming in as a kind of an online emission. So in terms of the offline emissions, though, a lot of the gas phase, sulfur, and biogenic volatile organic compounds can potentially be read in as offline emissions. In terms of sulfur dioxide, a fraction of the sulfur dioxide gas will be assumed to be emitted directly into the particulate phase. And that's because we have, there's a lot of, you can imagine this kind of grid across the world. There's lots going on within one particular grid cell in these emission inventories. So we might assume that some of the gas phase SO2 that's emitted has already formed particles, and so we need to put it in as a primary emission. I think the other things just to highlight are black carbon and organic carbon. There's a combination of sources from fossil fuel burning, from biofuel burning, but also from biomass burning. So fires around the world, there's different inventories that you might get emissions of those from. And again, that's something where through time we'll move to a way of modeling these things where we've got kind of interactive representations of fire, that we can actually take those emissions of black carbon and organic carbon will come directly into the model. But when we're starting off, a lot of the time we'll be reading these emissions in. A couple of the emissions that will be calculated online, because they're controlled by the kind of atmospheric conditions or the meteorological conditions, are, for example, sea spray, which requires the wind speed in the model in order to calculate what the sea spray emission is, and that sea spray is emitted straight into the accumulation and coarse soluble modes of the model. Similarly with mineral dust, it's again dependent on the level of kind of interactivity of your model components. You might have this coming from the land surface, but otherwise it might be that you've got an input that gives you the kind of potential for mineral dust emission, and then you still need to know the wind speed in order for the model to simulate an actual kind of emission of dust into the atmosphere. And so as I said here, dust might be carried in 6 bins that are not interacting with the other species, and that's because of this kind of separation of dust still being looked after essentially in the classic aerosol scheme rather than in UKCA mode. But that will change. So in terms of the emissions, we can kind of see where different things might be might be coming from. One of well, in fact, the only way that new particles are actually created in the atmosphere is from the nucleation of particular gases that are emitted. And that's a really important process that happens in different parts of the atmosphere and actually needs to be represented in different ways in different parts of the atmosphere. So in the upper troposphere, we can represent essentially the nucleation of semi-volatile gases to give us new particles. And for a long time, that's kind of how this process was represented. But people started to realize that actually down at the surface in the boundary layer, that wasn't giving us enough new particles being created. So like those size distributions I showed at the start, if we see a big spike in the number of very small particles, we know that they must be being created. They're coming from somewhere. And what this chart at the bottom is showing is, over time, at a particular location, the diameter of particles is being shown on the y-axis, and then essentially the concentration of particles at that size is indicated by the colour. And it shows that over time we're seeing this kind of essentially a burst of particles coming in at a small size and then growing to larger sizes. So they're essentially being created and then growing to a larger size. And in UKCA at the moment, there are switches that would enable you to choose which of these nucleation mechanisms you want to include. So for a long time, this process of new particle formation in the boundary layer was being represented just in relation to sulfuric acid. So we might have an equation that was essentially just some kind of scaling of the concentration of sulfuric acid, and then we assume, okay, we'll get some quantity of particles that relates to that. But over time, there's been more and more work. So the references to Metzger and Riccobono and Kirkby all relate to work that has been done over the past sort of decade, looking at which other gases might be involved in this process, and finding that actually the oxidation products of organic species might be playing an important role in this as well. So there's been a lot of effort to try and really pin down exactly which species are contributing to this process, and then to try and represent that process of particle formation in the model. And you can imagine that the more different things that are involved in that, the more different emissions you need to have right, the more your transport needs to be right. You need to get all those ingredients at the right concentrations into the right places in order to represent that successfully. Yeah, so as I say, when you start looking through UKCA, you might find some switches, and I think they're called BLN, with different numbers, and that's what they're referring to, basically different ways of representing this process. So once they're formed, unfortunately, depending on how much you care about these nucleated particles, only about 10% of them actually make it to the size of 100 nanometers. So that would get them into the accumulation mode. This is important because this is the size at which they're mostly starting to affect the climate. So that's why we're really interested in, or you might see people talking about things at 100 nanometers quite a lot, because that's an important size for that reason. So there's a couple of things that can happen to them on the way. So I mentioned the oxidation products of organic species. So in terms of UKCA mode, there are two kinds of gases that can condense onto our pre-existing aerosol particles. So either oxidation products of biogenic volatile organic compounds. So these are things like monoterpenes and isoprene. Once they're oxidized in the model, they create something called SEC-org, which I think you've got an exercise that involves doing some tinkering around with how SEC-org is produced and what it does, but it's essentially a tracer to just represent those oxidation products. And that secondary organic material can condense onto existing particles. So that's what's happening on the left-hand side here. Sulfuric acid can do the same thing. So we end up with our existing particles essentially getting coated by these kind of soluble materials. which helps them grow to a larger size. So they don't necessarily stay in a nice little quadrant of the circle like that, but that's just to represent that they are kind of adding to the particle and increasing its size, but they don't actually increase the number of particles. They'll just grow them to a bigger size. And this is a really important process because it's probably the main way that our small nucleated particles are growing to a size where they're big enough to act as cloud condensation nuclei. The other important consequence of this is that by having these gas phase soluble compounds condensing onto insoluble particles, that process, after a certain number of time steps in the model, will transfer particles from the insoluble mode to the soluble modes. So once they get a certain amount of soluble material in there, a fraction of the material will be moved over to the soluble mode. The other thing that happens alongside condensation is coagulation of particles. So they're all in the particle phase, but essentially smaller particles kind of banging into larger particles can cause them to coagulate. So again, this ends up giving you larger particles, so it's another way that particles can grow. But because you've got, you might have lots of smaller particles coagulating with a larger particle, you end up with fewer particles overall, but they are bigger. So your mass is the same, you've kept the same amount of material, it's just distributed across fewer particles. And again, this is a way that the composition of your particles might change through time. So there's a couple of things to say about how aerosol particles are removed from the atmosphere. So what we've looked at so far is where they're created, where they're emitted from, how they might be transformed or kind of moved through the size distribution, but they don't all just accumulate there forever. They are removed by various different processes. And so starting with the processing that happens in clouds, there's lots of reasons why we might be interested in the activation of particles to form cloud droplets. So this essentially happens when soluble particles of a certain size act as the kind of nucleus for a cloud droplet to form around. That's important for understanding the climate impact of aerosol particles and understanding how kind of the brightness of clouds change. But there's also an element of aerosol processing that happens through this kind of interaction with clouds. So the particles can actually grow in size, and then as the cloud evaporates, those particles can actually come back into the particle phase at a larger size. And this can create the sort of bimodal distribution that we saw in some of those early size distributions, because essentially your smaller particles are kind of being transformed into larger ones. And so that's one of the ways that particles might end up being removed from the atmosphere, but there are others as well. So Alex mentioned dry deposition from the perspective of gases, but it's also important for particles, as you can imagine. This is only happening in the layer of the model that's closest to the Earth's surface, and it depends not only on the size of the particles, but also on the surface over which this deposition is happening. So Alex had a diagram where you were looking at kind of resistance to various processes, but if you imagine the tree he had on that diagram, it's all about really the roughness of the surface. So if you have something like a forest that's quite rough to the atmosphere, you will get a greater amount of deposition to that surface. So again, this is a process that depends on us knowing not only what's in the particle phase, but actually what's going on the land surface as well. So this could be something that is, we might have a representation of the land surface that's just read into the model, but we might be running the model in an interactive way. That means we're actually looking at how the land surface is changing over time and understanding how that affects the deposition as well. The sedimentation and gravitational settling is essentially the force of gravity on particles that will be pulling the largest particles out of the atmosphere. But again, it's only removing them from the atmosphere in the lowest level. Otherwise, they're just settling to the next lowest level. There's two processes that are, so that the top two you could call dry deposition, I think, and the bottom two are related to clouds, so not dry. So within a cloud, I mentioned previously that you can have this processing that actually kind of gives you larger particles. The other thing that can happen, though, is that if the cloud rains, then you're going to lose your particles from the atmosphere. So again, that it's size dependent and potentially dependent on the composition as well. That's once they're in the cloud. Below the cloud, in the atmosphere, if you're below a raining cloud, you can imagine that it's essentially a process of being kind of washed out of the atmosphere if there's raining clouds above where you are. And again, this is dependent on the size of the particles, the extent to which they are removed from the atmosphere in that way. So hopefully I've given you a bit of an overview of those different challenges that we would face when trying to represent aerosol particles in the atmosphere, where they come from, how they are transformed, and where they end up. But we very rarely are just interested in the amount of aerosol in the atmosphere in a particular place. We want to know really how that is affecting other things. So it's important for these processes to be linked to the rest of the model. And so I mentioned that I would show you some of the kind of the subroutine names. So within UKCA, there's a subroutine called UKCA aerostep. So this is where all of the stuff that I've been talking about today is kind of done within that particular subroutine. So you can see things in here like prim SU is where the primary emission of sulfate is happening, cloud processing, dry deposition, condensation, nucleation rate, coagulation. So all of those things are represented in their own little subroutines that the model will step through and kind of work through each time step to see if things need to be updated. But once we've got the kind of how that series of processes has changed the size distribution, we might need to know something else, like how it affects things like cloud droplet number. So this is done in a sub-routine called UKCA activate, which is essentially all about taking that aerosol size distribution and working out how many of those particles are going to activate as cloud droplets. And there's a reference there to a paper where that was kind of initially developed and incorporated into the model. So that's telling us that for any given location or for any particular size distribution, do we have particles that are big enough and soluble enough to activate as cloud droplets? And then that will get taken into account in the bit of the model that's interested in kind of balance of radiation, because if we've got a lot of cloud droplets, that'll make the clouds brighter and feed into that radiation balance. The other element of that is called UKCA rad air. So this is where all of the information about how reflective or absorptive our aerosol size distribution is. And so what the little map on the left is showing is the aerosol optical depth at a particular, well, it's probably a global average, an annual average actually, sorry, from the glow map mode model. So you can see the regions where we've got particularly high aerosol optical depth tend to be where there's a lot of dust, or where there's a lot of anthropogenic pollution, where we might see high aerosol optical depths. So that's essentially, again, it's taking all the information from the aerosol modal subroutines, and then it's working out how that's impacting the incoming and outgoing fluxes of radiation. And I just wanted to finish really by coming back to this initial initial slide where we were looking at how all of these different factors are affecting the climate and have affected the climate from the pre-industrial period to today. And you can probably get a sense of just how complicated it is to try and work out what this number is for aerosols, because of all of those processes that we've got to try and represent in the model and try and get right, or get right enough to give us this answer. And you can see, I think, why you might end up with such a big range, because all of these models, the range essentially comes from different modelling groups around the world doing their own version of creating UKCA, coming up with their own way of representing those processes, and then working out how much of an impact they think aerosol particles have had on the climate. So you can see that there's so much going into one of those calculations that could vary. And so it's already, even at this point in time, is an important thing for us to understand and try and get right. But on top of that, what these plots are showing, this was from a recent paper that was looking at changes to aerosol in the future, essentially. And some of you, I'm sure, will be familiar with these shared socioeconomic pathways, SSPs. These are basically different kind of future projections that are used to try and help us kind of evaluate what might happen in the future. With black carbon emissions on the left and sulfur dioxide emissions on the right. And you can see that for both of them, there are scenarios in which those emissions might fall rapidly, but there are also scenarios in which they might continue to rise. And there's a lot of variation between the kind of extremes of those scenarios. So if we don't fully understand exactly how much the emissions we've had so far have affected the climate, we've now got to try and apply all that understanding to this kind of range of potential future emissions, which is huge. So in terms of kind of working on developing these models and really trying to get them to a point where they're representing reality as accurately as possible, I think it's going to be a really important challenge over the next few decades. And I know Alex was kind of saying, we shouldn't get too hung up on trying to get our Lego model to look exactly like the work of art, which I agree with. But if the work of art is what we've got to kind of assume the future is going to be like, then I think we do need to get our Lego model to be as good as we can. So yeah, I'll just finish by kind of highlighting some of the key points from this. And as I say, I think depending on exactly which area of UKCA you are working with, or UKESM, or which part of chemistry or aerosol you are looking at, you might never think about some of these things ever again, or you might really focus on one of them and kind of get into it in detail. So it's all about really understanding that it's a framework for you to use to look at the particular bit that you're interested in. So GLOMAP mode is the aerosol model within UKCA, and it can have 7 of these log normal modes. The standard model at the moment is generally treating these 5 species, but that is subject to increase. But you can alter the setup to include as many modes or species as you want. It treats the main microphysical processes that control what ends up in the atmosphere, how it's processed, and how it comes out again. And it's coupled, depending on the version you're using, it's coupled to a greater or lesser extent to other parts of the model. And the final point here was just to say that it's a working model in the sense that it's continually being updated, evaluated, developed, and it does compare well with observations. But of course, you might be the first person to try and compare the very particular bit that you're interested in to observations. So this is a continual kind of effort to try and make sure that is the case. And I've got a couple of references at the end. So when Luke shares the slides with you, you'll be able to get these. But I think in terms of understanding of the science, or if you're trying to work out, you're looking at the code, you're trying to work out what's going on in a particular subroutine, this the GLOMAP mode paper from Graham Mann in 2010 will give you the detail of what different subroutines are doing. The second paper is from Jane Mulcahy that came out a couple of years ago, and she'd evaluated essentially UKCA within UKESM. and compared it to observations. And then I just mentioned a new textbook that's recently come out that kind of tries to really capture a lot of the key processes that are happening in the aerosol, in the particle phase in the atmosphere. So it's not related to UKCA specifically, but if you're working on aerosol, it's probably a good place for some to start in terms of learning. So I'll be around for the rest of the day, so I'm happy to answer questions about aerosol over that time. But if anyone's got any questions now, then also happy to answer. Thanks.
Really interesting. I mean, I've done a lot of work with aerosol with Cat and still learning more about it. Anybody got any questions?
Normally, when you show, for example, the cause the subroutines emission first, then the chemistry, then the aerosol. So that means glow map don't change the chemistry part at all, or no interaction.
Ooh, that's a good question.
So if you look, so this one. So that means you just get the emission first, then chemistry.
Well, so the aerosol. But I think the aerosol is happening on a shorter time step. So that's happening kind of multiple times, and then you go back to the emission and the chemistry again. So it's not that it's not affecting the chemistry, but it's just that it's being affected by what happened in the aerosol previous time step, I think.
So that means, for example, if you have a glow map in the UPSM or UKCA, if any changes for the aerosol property or something, so that don't change the younger layer or strategy layer.
For the stratosphere.
Yeah, much a little bit more.
Yeah.
I'm not clear. So.
Well, we should go offline, but I mean, I was thinking about the first question. I think inside UKCA, it does change H2O2, doesn't it? There are some details of certain. Yeah, I think like certain oxidants can be modified inside the glow map code that then gets passed back. But I think it's like previous project. There was this process split. So when UKCA, so when glow map's doing its thing, nothing else is changing, but you sort of time steps are short enough that things are separating to cleanly.
Yeah, maybe the stratosphere bit. Yeah, we can come back to it. Yeah.
I'm wondering about the moments. I thought it was quite interesting in the business like. Is there any reason for choosing 7? Is that just like the number that worked, or like choose more with it more accurate?
I think possibly a bit of both. So it's a number that's worked in terms of when people have. So you wouldn't need to have 7 necessarily. That's just because we've got 3 that are soluble. 3 that are insoluble of the 4. So you could. There's quite a few models actually that use this 7 mode kind of underlying framework. So it's not. I think really it's when you look at the size distributions that are observed, they do map onto those modes really nicely, and that's not. I don't think that's for any particular reason. I think it's just that has kind of, that particular number now does seem to work quite well. So yeah, I think you'll always get a more precise description of the size distribution with kind of narrower bins if you were doing it like that. But I think broadly, the kind of 7 modes gives you a good enough representation. Yeah.
I have 2 questions. The first was, I might have misunderstood this, but is it only secondary organics that are coagulating?
No, sorry. So that was it. They're condensing. Yeah. So the secondary organics are condensing, so is sulfuric acid. In reality, there would be more than that, but that's what we're treating in UKCA. The coagulation, though, can be any of the particles. So that was just because I was representing it in the same kind of schematic, I think. But it doesn't have to. So it can be let's say smaller particles in your Aitken mode could coagulate with something in the accumulation mode, and then their mass would get transferred into the accumulation mode. So that's less about the composition, when it's coagulating.
That kind of leads into my second question, which is the five categories that compare with models, so sulfate, organic, lactose, and products. Can there be coagulation between those?
Yes, yeah. So when you've got a mode, everything within the mode is assumed to be internally mixed. So every particle within that mode, as far as the model's concerned, is made up of a bit of all of those components, not separated out. There are some models that will track kind of components individually, but for UKCA, what it's carrying is the number of particles and then the amount of each of those components, and it's assuming that they're kind of distributed evenly. So when you get that coagulation, it's assuming that each particle is just made up of a combination of all of the components. So that can be, sometimes that's true, that's a good representation of reality, and sometimes it's not particularly. You might have very pure particles that are made of one thing and perhaps coated by something else, so that complete internal mixture is not necessarily always a good representation. But in terms of what's going on at the kind of grid cell size, it's a good approximation.